Other questions?
Yeah, I got a question.
Yes.
What section are in the book are we at right now?
What section?
Yeah.
I don't have textbook with me now. Basically, you read the notes. You see based on what the page I finish it should trace back where the book is. To me, that's straightforward.
Right. Just just need to remember what page to open the book in.
Okay, then when you attend a lecture, you should be able to know where we end the last time. Or every lecture class, you take just a mark, say, oh, we finished page what? So, okay, that's
Okay.
that's to me it's so straightforward. Okay, so the end actually, well, I can go back sort of the review what we did at the end towards the end of the class. Actually, the last class we finished page 19. Okay, so that's this page
Okay.
19. Yep. So the PN junction under zero bias, we call that equilibrium. So I can move back one page, say, okay, review the page 18. So we talk about the first electronic device, semiconductor device, that's PN junction. Okay, material structure-wise, it's a two region of material. One region is p-doped region. Another region is the n-doped region. Right? Just okay. Let's see. I can change the mouse. Right, p region, n region. Okay, we name this interface as x equals spatially x equals 0 coordinates. Okay, because this region have majority electron, very little electron in this region, so electron will diffuse from n region to p region. Electron will diffuse from n region to region. Okay, likewise, in the p region, you have majority carrier, a lot of holes, but very little holes in the n region. So the holes will diffuse from the p region to n region, as illustrated here. Right, so the diffusion. So next page, so where we end last time, is the what happened after this called the diffusion process begins. Okay, repeat. Okay, diffusion occurs. The electron near the interface, electron diffused across into p region. Holes in this near the interface region diffuse into the n region. But what's left will be you expose the so we call this region called the depletion region because the mobile electrons diffused, mobile holes diffused. What's left will be exposed ions or atoms. Okay, in n region, once electron diffuse across, you're left with positively charged phosphor atoms. In this region, as holes diffuse into n region, what you expose here left will be the negatively charged boron atoms. These are space charge regions. We call the space charge regions. Positive charge in this side, negative charge on this side. All right. They're non-mobile. Those ions are heavy atoms, non-mobile. Mobile carriers already diffuse away. So this region, we call that the space charge region. We also name called the depletion region, right? Very thin fraction of micron. Well, the next consequence is once you have a space charge region, positive charge on this side, negative charge on this side, then by the physical law, there will be an electric field, okay, created pointing from positive charge to negative charge. So that's the internal field is the field, E field here. Corresponding to this E field, we can also associate it with a space, the potential barrier, P, as illustrated this.
Oh,
Yes, you have a question? All right, so no, I'll continue. So the electric field pointing from positive charge to negative charge, the potential will also build up, okay, from the low end at the negative charge and raise to the high positive charge, raise to high the barrier. So this shape. So then we'll see the next consequence. The next one is that once the internal field or the potential barrier is built up due to the initial diffusion, then the further diffusion will be difficult because, say, for example, do you have a further diffusion of the holes get to the other side? Well, once the holes try to diffuse, once it entered the space charge region, you see this potential, boom, will be kicked back, pushed back. The electrons in N region be further diffused? Once electrons try to diffuse, once get this region, will pull back by the electric field. Again, difficult. So this potential barrier acts against the further diffusion of majority carriers. So that leads to the movement of diffusion, which creates we call the diffusion current, and that diffusion current is small because of this barrier in action. So we talk about what happened to the majority carriers. So next, we're looking for what happened to the minority carriers. Minority carriers in these regions are the, let's put this. Minority carriers in N region are the holes. Once the holes, by thermal Brownian motion, get to the edge of this space charge region field, this positive charge will be pushed by the electric field to this side. And likewise, minority carriers in the P region, once they wander into the edge of this space charge region, the electrons will also be pulled by electric field across the space charge region, get to the other end. So we have this situation occur, minority carriers be swept through space charge region by the internal electric field. This movement resulting in what we call the drift current, but the amount of drift current also is small because what? They are coming from minority carriers. So we know the amount of minority carriers is very small, so the correspondingly drift current amount is very small. So what's the overall current or net current? So net current, what we call the I of D, is indicate I of D, the direction is pointing in this way and coming from the P region, getting into N region. So that's the I of D, the diode current. So diode current will be summation of the contribution from the diffusion and summation of the contribution from the drift. However, diffusion and drift current pointing into opposite direction. So there's minus sign here. So the ID actually line up with the direction of the diffusion current. So this ID current line up with this diffusion current direction. And under zero bias, when there's no external battery or power supply put into this wire, so you have a zero bias, then drift current and diffusion current cancel exactly, so resulting a zero external current. So that's under zero bias, you don't see any external current in this PN junction. So that's what we discussed last class. Any questions? If no questions, so let's say this is our baseline under zero bias. Yes?
I'm a little confused on what happens when the flow of electrons crosses the midway point inside of the PN junction. If the
Okay, you have one part question and the second part question. So I think your confusion occurs at the second part. Say that what I say that electron in this region diffuse, they diffuse all the way into this region. So you don't have an electron left here. Do you understand? Because the second part of your question say, once the electron diffuse, you don't know what happened of the electron in the at the cross section area. No, once electron diffused, no electron left in this region. That's what we call that the depletion region. No mobile electron and holes in this region. Did I answer your question? Hello? Hello?
the bit that's confusing me is if the reason that electrons can't flow backwards is because the electronic field will oppose the motion. But after it crosses the midway point, even flowing the correct direction, why doesn't the electric field oppose it?
Here we talk about, okay, you talk about electrons. Okay, as a substance, you can say that's electrons. But my point is these electrons coming from the carriers in N region or coming from the carriers from P region. They're different electrons. You understand?
I'm sorry, I'm a little confused, but go on. That's okay.
Okay. So what we talk about is the diffusion of majority carriers. What we're saying is that these potential make the diffusion of these electrons difficult. But this electric field will pull this electron towards this end. So that's the action of a potential barrier. Okay? So the electrons coming from different regions. For the electron from this region, the potential barrier will against the diffusion. For electrons in this region, this potential barrier will try to pull to this end. But the potential is created because you have initial diffusion. Okay, so don't confuse the initial diffusion and once diffusion create a barrier. What's the action? Okay, afterwards. So it's a little bit. You can say a little bit. Okay, sort of chicken and egg, but here you have the distinction. What's chicken first? Okay, chicken is you need initial diffusion to create the potential barrier. But once you create potential barrier, diffusion of these electrons will be difficult. But these electron minority carriers can get through. Okay. So next is the situation, what we call that the reverse bias or p-n junction under reverse bias. So what's the definition of reverse bias? When I say a bias means you put the external voltage source connect to this p-n junction device. And the definition of reverse bias configuration is such that the positive terminal of the voltage source is connected to the N side. The negative terminal of the voltage source is connected to P side. That's the definition of a reverse bias configuration. Okay. Well, let's see any consequence of when we put a battery configured this way. Well, this battery, you have a positive end this side, the negative end this side. It will exert an electric field associated with this battery. And that electric field, we call that the applied electric field. Applied electric field is east of A. So this internal field created due to diffusion. And this east of A is the electric field created by the external bias voltage. Under reverse bias configuration, the internal field and externally applied electric field pointing in the same direction. Well, that just enhance the electric field, overall electric field in this space charge region, or the potential barrier gets increased, gets higher. Stronger potential barrier. Okay, we understand the potential barrier's action, so that means, depletion region increase, potential barrier gets higher, but then diffusion of majority carriers get even worse or more difficult because the higher potential barrier, the more difficult diffusion of majority carriers. So diffusion of majority carriers become more difficult. So that corresponding to diffusion current will get a decrease, become very small. It begins to be very small, and then it becomes even more small, even smaller. In this process, the drift current remain about the same, not sensitive to the external bias voltage, only sort of weakly sensitive to the temperature. But temperature, we kind of approximated keeping it constant, so the drift current amount nearly unchanged. So let's see what's the balance or imbalance consequence to the external current. External current still defined as a diffusion current, subtract the drift current. Drift current almost unchanged, diffusion current gets smaller. So have an imbalance. So that imbalance says external diode current, you have a non-zero external diode current, which is negative, okay, inside. So what's negative? Negative means what? The reference direction of ID is labeled in this way. If ID value is negative, that says what? The actual current pointing in this direction. So actual current flows from this end to this end, which is consistent with the polarity of the external power supply polarity. Yes, now under reverse bias, we have a non-zero diode current, but this current is very small, because what? To begin with, drift current amount is small, diffusion amount current is small. If this diffusion current is very small, then you're left with drift current. It's even smaller, a bit smaller, just small. Any question? Okay, so let's briefly summarize. On the zero bias, the current is zero. On the reverse bias, you do have some current in the reverse direction, but that amount is very small. Okay. Now we're ready to look at the situation on the forward bias. It means the external power supply voltage polarity flipped. Plus sign of a voltage polarity applied to the PN, and negative polarity applied to N side PN junction. Well, corresponding to this power supply, the applied field EA pointing to this direction, which is opposite to the internal field created by the diffusion. Okay, these two fields tend to cancel each other and make the potential barrier lower. Well, as you lower the potential barrier, that means that diffusion becomes easier. When the diffusion becomes easier, then the corresponding diffusion current gets increased. And this increase can be very large. Almost there's no limit. The larger the voltage power supply voltage at the external increase, and the diffusion current will get increased. But at the same time, drift current remains almost unchanged. So finally, you also have the imbalance of the overall current. Diffusion current much outweigh the drift current. So you have a plus sign. So plus sign means diode current as indicated in this direction, diode current indeed going this way. Okay. Consistent with the polarity of your power supply voltage. Plus sign, the current going this way. But unlike a reverse bias, this amount of current I to D can be very large. The reason very large means what? There's almost no limit on how high the diffusion current can go. Right? So once you lower the potential barrier, the diffusion current can go very large and it create a positive diode current in this direction. Any question? So this is qualitative.
I have a quick question.
Yes.
So for this PN junction, does this apply to conductive elements in general or specifically to silicon?
Well, no way is the same as conductor. Okay, it's go back to why, in the first two lectures, we talk about the semiconductor material. Semiconductor material just different from a conductor material. So period. Okay? Has nothing to do anything similar to the conductor. Conductor has no such property. If conductor has this property, why we need to semiconductor business? Right? If anything, the conductor you learn in the 306 can do the work. Why we go do the hard source to create a semiconductor material and build a semiconductor devices, right? So this sort of a ground level, okay, no way a conductor material can accomplish those properties or the behavior. Did I answer your question?
So this is a built property, as in like we made this happen.
First, semiconductor material, particularly you create the N material, you create P material, exactly is by design. You create this material. They are not naturally occur. Otherwise,
Okay.
why we have needed this in the industry business? You need to
Alright.
fabricate, design, and fabricate it. Did I answer your question?
Yes.
Right. So that's material-wise, you need to fabricate or design. This is a new type of material. And secondly, the diffusion does not occur in a single crystal. It occurs into the PN junction. So PN junction is the first semiconductor device we learned made out of a semiconductor material. But it's not a single piece of semiconductor material. It's a two pieces of semiconductor material put together. This is another device design aspect. Okay, diffusion does not occur in a single piece of a P material or N material. Only occur here when you have a PN junction. You have uneven distribution of holes electrons across the whole device or across the interface. Right, that's another design or fabricated consequence. Did I answer your question?
Yes.
Okay. Right. So this is totally new, right? So different from the things we learned from the previous courses.
Professor, I have a question.
Yes, please.
So, if I understand this right, so during the diffusion process, the minority carrier concentration is increasing on both sides. And is that movement of electrons and holes causing the current?
Okay, let me pick up your statement, okay, to see if we, basically, let's say, hopefully our understanding is on the same page. You're saying is, under what, reverse bias?
Yes.
And then you're saying the minority carriers get crossed, so have more, okay, you add a little more minority carriers in the N region, that's what you refer to?
No, I'm sorry. The forward bias. So that's when the minority carrier concentration increases, right? After the diffusion process.
No. Read every line of this statement, okay? The applied electric field cancels the internal field. No ambiguities, right? First line, right? The
Yes.
second line, the depletion region decrease, potential barrier lower. There's no confusion in this line, right? Okay? No. Okay, what's the third line? Third line is the diffusion of majority carrier become easier. Did I say anything about minority carrier?
No.
No. Okay, so when in this description, okay, all we talk about is what happened to the majority carrier. What happened to the minority carriers is hiding or the sort of summarizing this phrase. Drift current almost unchanged. And it is the minority carriers in this slide contribute the drift current. So the drift current or the minority carriers was not influenced much in this process. You influence majority carriers, but minority carriers didn't get much push or drop. Did I answer your question?
Yes, thank you.
Okay, so put it again. Next phrase, next one is more summarizing. Here, all previously I described the qualitatively. Let's go more quantitatively or mathematically. Okay, direct quantitative features. Again, this is not you don't see that in the textbook. I summarize that for you. There are a few things you need putting together. One is once a PN junction at the interface, you generate a potential barrier under zero bias. This potential barrier with BI is dependent on the doping concentration of the acceptor and doping concentration of the donor on the N side, on the P side, and also kind of dependent on the temperature or the carrier densities as calculated from the intrinsic semiconductor material. This is temperature dependent, this is temperature dependent. Okay, so that's okay. On the zero bias, how high the potential barriers you can get, you can calculate that by this formula derived from the physicist. The next couple lines is what I kind of re-enhance what I explained to you. What's the diffusion current? Diffusion current coming from movement of majority carriers. Okay, they are sensitive to potential barriers. And these potential barriers is strongly influenced by the external bias voltage VD. And how strong it is? Okay, it depends exponentially. It is a diffusion current, okay, is related to the under zero bias, but if you put in a non-zero, okay, bias voltage V sub D, and this is exponential. So you can see that if under zero bias, VD is zero. When VD is zero, this factor is 1. So diffusion current goes back to diffusion under zero bias. If VD is negative under reverse bias, this factor can drop to 0, can be negative. Not negative, this can go to almost 0. Diffusion is so difficult. But on the other hand, if the V sub D is positive, and this exponential term can shoot high, huge. That's what we say. Diffusion under 4 bias, you can go very large. How large? Increase exponentially large. How about drift current? Drift current contributed from minority carriers. Okay, they're mostly influenced by temperature, but not influenced much by the bias voltage. So the drift current nearly remain constant, unchanged to the under zero bias. And at a zero bias, drift current equals the diffusion current mathematically. Any question? So this is kind of a more specifically mathematically, how do we describe what happened in the PN junction? Overall diode current, ID equals I diffusion, substitute I drift. You substitute the I diffusion in this expression, you substitute I drift in this expression, you can simplify into this form, final form. Okay, so kind of say we are quickly sort of semi-wavily derived the current and voltage relationship in this formula. Okay, in this, okay, finally, I sub S, okay, really this one just renaming what's this factor. And this factor really is what later we will say maximum reverse bias current. Okay, it is why we call the maximum reverse bias current. We are looking for under very strong reverse bias. Okay, then VD is almost infinity. When VD is almost infinity, this factor goes to 0. When this factor goes to 0, ID equal to minus IS. So it's a reverse bias current minus sign, and you get a maximum because there's full contribution I sub S or ID coming from movement of minority carriers, this factor. So maximum reverse bias current. Any question? Okay, no question. Now this gets back to what the textbook, I have a few graphs to tell you. So that I summarize this as a PN junction diode device, the PN junction diode device law. What's device law? Current voltage relationship. Okay, remember? On the first day, on the second, okay, diagram, I said, okay, flip, okay, second diagram. I said here, in 314, we'll keep using the same Kirchhoff law, but we will learn new device laws. So what's the new device law? Device law is the current voltage relationship. And we're going to learn new device, diodes. So we're going to learn current voltage relationship for diodes. Okay, so the first day I said, we're going to learn that. And here we are. Okay, so let's flip back to this page. Now, finally, after all the preparation or the physical foundations for the semiconductor material and semiconductor devices, and we come out with the current and voltage relationship for PN junction diode, which is summarized or expressed mathematically in this form. Okay, so this red. In this way, there's a small modification. There's a small n put in the on the exponent of the denominator. This is named as emission coefficient. They say, okay, what we previously derived is more like a little crude derivation, but more mathematical derivation is material dependent and so on and so forth. The fabrication, how good the fabrication property process is. So this factor n is ranging from 1 to 2. It's a small, okay, not small. It's a factor. If it's equal to 1, then that's completely the same the formulas I gave here, right? But it's just slightly deviated from 1. Okay, in our rest of the book discussion or homework, we can assume n equal to 1, unless otherwise state. When I say unless otherwise state, I can give you a heads up. Next week's lab is about the you really learn the diodes voltage current relationship, and you're asking to fit your experimental result with the theoretical formula. And well, you can, to begin with, you can use this formula. But if you find some deviation different, slight different, what you can do is adjust the value of n to make the fit. So that's what I say. So summarize this wording. Diode is a two-terminal device, right? This two-terminal. Externally, if you view this as a black box, this is one terminal, this is the other terminal. Current coming into this terminal and get out from the N terminal, coming in from P terminal, coming out from N terminal, as we define the diode's current reference direction. Okay, how about the voltage of diode? Then is a plus sign, is defined and line up with the P material. Negative sign, terminal line up with N material. That's the definition of polarity of this voltage. And this is a symbol for this PN junction diode. It's triangle with a bar. Okay, again, current coming in from the triangle side and leaving from the bar side. And polarity of voltage on the diode, plus sign is on this side, negative is on this side. And because we defined this polarity of the voltage and reference current direction in this way, so we are able to write down the current voltage relationship by this formula. And also the diode of current power is a VD. So what's V? Is a V of the diode. What's DID? VI. Sorry. Power equal P equal to VI. The voltage V is the VD diode voltage. Current ID is current diode. Look at here. In this equation, by default we use a plus sign. By default we use plus sign. All right, that's by default. You learn from 306, there's a very important convention called the positive sign convention. And usually when you arbitrarily define the voltage polarity or current direction, you have to make sure that voltage current relationship follows the positive sign convention properly or not. Sometimes you can put a plus sign in there, like Ohm's law, plus sign. And sometimes that Ohm's law, you need to put in the negative sign. Likewise, power nominally is V times D, but sometimes the way you define the polarity of voltage or the way you define the current direction, you need to put a minus sign here. But for diode, I here give you by default the plus sign here. It is because what? The definition of current direction and definition for voltage polarity consistent with plus sign, the version of positive sign convention. Okay, so that's very important. You need to put the diode direction and diode voltage polarity in a correct way. This relationship is this shape. Right? That shape, we have not seen that before. Only, familiar with device law we learned is Ohm's law. Ohm's law is what? Current and voltage are proportional to each other. Basically, it's a straight line across a zero. For the diode, it's totally different behavior. If you bias sufficiently on the full bias region, you may get a large current. If you bias in the negative bias, you have a very small negative current, not equal to zero. This is we cannot magnify this. This can be on the order of 10 to the 10, very large. The 10 to basically a fraction billion difference between this current amount and this current amount. Okay, and they cross zero here. Any question? So we learn a new device and we learn a new device law. It's a two-terminal device, but the current voltage relationship is so nonlinear. Any question?
Professor,
Yes.
can you say something about the I sub d is equals to negative of the reverse bias saturation current right there?
You mean this word, this part?
In the graph,
In the graph?
yes.
Oh, actually, almost there's no way I can resolve this. But let me just use the mouse pointer to show you what actually is. All right. So on the 4 bias, you have a large current, and then once you reduce bias, current reduce, and then reduce almost very small. At the 0 here, it exactly crosses 0 current. Okay, so this is the positive current, very large positive current, very small positive current. It crosses 0 at this point. But once it crosses 0, the current becomes negative, but just a very, very tiny, small below negative current. Okay, so this one. Let me see if the other one. Oh, okay, here. Okay. Later I will use this graph. I can tell you what looks like 4 bias, 0 bias, reverse bias. Did I answer your question?
So the reverse bias saturation current is equals to the diode current at some point in the negative region.
The maximum negative region. So basically, later we talk about this reverse breakdown process occur. If you don't consider reverse breakdown, previously, this graph, you can think this is going this way, and this one just into here, unchanged. Why is it unchanged? Because this term goes to 0. Once this term goes to 0, ID equal to minus IS, unchanged. But IS is very small. Actually, it's a amps to picoamps, 10 to the minus 10 to the 10 to the minus 12. Very small current. And in the device, we can call that a dark current. Okay. Did that answer your question?
Okay, yes, thank you.
Right. It is maximum under reverse bias, but nonetheless, this amount is very tiny. Picoamps. Okay. Okay. Normally, you talk about microamps or milliamps or amps. You ignore that, basically. Compared to this current and this current can be ignored. Sometimes, even you don't ignore that, you call that current a dark current.
Professor Yan,
Yes.
I had a question on that graph there. I can see
Yes.
why the current is very close to 0 when we're in the reverse bias. But why, when we go positive on the voltage, does it take like until we get to like 0.6 volts to get like shooting up in terms of the current? Like, why don't we go up from 0 like immediately after we go positive on the voltage?
Okay. Depends on the view you view, okay? You view close to this region, or you view when the current can actually shoot very up. When the current can go to very shoot up, I will tell you, okay, this current can shoot up to microamps to milliamps. Okay, if the microamps is 10 to minus 6 amps, if a milliamps is 10 to minus 3 amps. But what IS is about? IS, I said, is on the order of picoamps, 10 to the minus 10, 10 to the minus 12. So you have how much? 6, 7 orders of magnitude between this one and that one. So this is kind of a really overview. If you want to view this amount of current, you really crush the magnitude of this one into almost 0. Barely you can recognize anything. So this is because you want to display how much current may occur, look like here, and how much current get to here. So that you have to compress this amount in order to display this amount. under the single graph. But if you want to view what happened, coming from the negative bias into the zero bias into the positive bias, locally examine this region, you really should magnify that region into this view graph. Did that answer your question?
I think you got it.
Huh?
Yeah, you answered it.
Right. So this is okay. On negative side, once they cancel, but once they quickly drop to zero, once it's exponential decay very fast, so you get to all the second term. But here, exponentially increase also very fast, outperform I sub S very quickly. Okay. So I answer your question, right? Okay. So it really depends on which portion of a behavior you are examining at. So here we said 4 bias, sufficient 4 bias, 0 bias, reverse bias, the device law, current, direct current, and direct voltage relationship is nonlinear, so new, so completely new. But hopefully we all understand where this relationship is coming from. Next page, I'll discuss the phenomena called reverse bias breakdown. Okay, so this reverse bias breakdown. Okay, first, we're talking about diode subject to reverse bias. Okay, first things first, subject to reverse bias. So here, now let me just try to help you. I don't want to squeeze. I sort of flip between the two pages. I have another version of the notes. Okay, so this is a reverse bias configuration. So reverse breakdown phenomenon occurs when p-n junction is under subject to reverse bias. So what's a reverse bias? Repeat. Reverse bias is this external field, the voltage, produce external applied electric field, and this field add up with the internal field become very strong, and potential barrier increase. We said that. So this VR is external voltage, but under reverse bias. That's what the VR says. So I'm using this VR. Reverse bias saying, previously we were saying, you have a much, much stronger reverse bias. This drift current goes to zero. Drift current goes to zero. Direct current just go to equal to minus IS. That's previously we just said. But that's very ideal. What ideal? Is under the condition reverse breakdown didn't occur. Well, here we learn the new phenomenon. There's another phenomenon can occur called the reverse breakdown. What that is, when the reverse bias voltage becomes very large, okay, VR is very large, there are consequences. Well, consequences, first of all, electric field in the space charge region gets increased hugely. But once it gets hugely, there are two effects occur. First, we call the Zener effect. So what's the Zener effect? Well, here says, covalent bonds are broken by this strong electric field. And electron hole pairs are created in the space charge region. So in this region, we have very strong space charge field. And this space charge field can strip the covalent bond in this region or break the covalent bond. Once you break the covalent bond in this region, you set the mobile electron and mobile holes free. And those carriers leads to or contribute to a large reverse breakdown curve. Okay, so that's a Zener effect. The second effect is this. We say that minority carriers in the P region will be swept by the electric field into this side. And minority carriers in the N region will be swept by the internal field to this side. But when they are swept, they are accelerated by the internal field. Well, as they cross, the minority carriers across this space charge region, they will be accelerated or gain the energy from the applied electric field. They gain the energy, okay, then they start to collide with the atoms in this region. When they collide, the atoms in this region, they collide or bump on the covalent bond. When the energy, the kinetic energy gained so high, they can break or kick out the electrons out of the covalent bond in this region again and generate electron and hole pairs. And this the collision process can be add-on. Add-on means what? When you click more electron out of the covalent bond, and they gain energy, they can kick another covalent bond and knock out the valence electron again and again. So that's avalanche effect. Okay, and the result is again you will have a large reverse bias. You have a large reverse bias current under reverse breakdown. So two contributions phenomena contribute to the large reverse breakdown current. Any question? So previously, we discussed this, current voltage relationship is a bit ideal. Ideal just says what? We have forward bias, that's fine. We have reverse bias, but before we reach reverse breakdown, the situation. Once we get to the electric reverse bias, the voltage is too high, the electric field in the space-charge region is so high, it will start to break the covalent bond in the space-charge region, and further collision of these accelerated minority carriers can knock out the electrons out of the covalent bond further, create even more additional electron hole pairs. Now, end result, you have a lot of charge carriers created under reverse bias breakdown, and that leads to a large reverse breakdown current. Any question?
Professor?
Yes.
So basically what you're saying, is my understanding, is that in the forward bias, you don't need a large voltage to cause current to flow.
No.
But in the reverse bias, normally current won't flow, but at very high voltages, current can actually flow kind of the wrong direction.
Not wrong direction, in the opposite direction.
Okay.
Yeah. You check once if the electron fall in this direction, the electron will move in this way, and holes will move this way. So externally, electron move this way, holes move this way, hole carries a positive charge. So externally, you have a large breakdown voltage flow in this direction. And this direction is opposite to what we define the diode current. Yes, in the opposite direction, not wrong direction, opposite direction. I don't call it wrong, but just opposite. But you're right in terms of the direction wise. Any question? Okay. So
I have a question.
yes.
So is this this reverse bias, is this the basis for how resistors are designed?
Resistor?
Like, since you need a high voltage to induce a current, and this kind of seems similar to what a resistor does, where it I don't know the right word for it, but I guess resists current or resists voltage.
No. Okay, so very different concept. As I said, in this graph, we discussed the new electronic device called a diode. And so diode has its own device law, means its own current voltage relationship as expressed in this way. This is a nonlinear relationship. They're nonlinear. You use the analogous of resistors. I commented before. Resistor is a electrical component we learned in 306. What's the device law for the resistor? Is Ohm's law. So yes, you kind of remember Ohm's law says the large voltage you have large current, small voltage you have a small current, right? That's what you refer to, right? However, that device law is a linear relationship. Current is proportional to voltage. It's a linear relationship, not a linear relationship. You don't have exponential term. Everything is linear. So linear means what? Voltage current relationship is a straight line across zero. Of course, the larger the voltage, you have large current. Small voltage, you have small current. You reverse voltage, you reverse current, but the current is as large as forward bias. You only reverse the direction. You don't change the current magnitude as you flip the voltage from one side to the other. Correct? But the diode is so different. You have a lot of current in this direction bias. You have a little current in this direction. So basically, later we'll talk about this. Just says what diode is behaving as a rectified circuit. In one way, you bias voltage, you can see the large current. In the other way, you bias voltage, you see very little current. So this has nothing like the resistor. What we're saying is that reverse bias means what? Nominally, by what the physics we decided up to this point, on the reverse bias, you don't expect much current at all. Okay? However, on the reverse breakdown, you do eventually see a large current. Is this behavior same as the Ohm's law? Ohm's law is this way. Is this Ohm's law? No. Right? So don't confuse that with Ohm's law. All we're saying is what? When you have a large reverse bias voltage, the electricity, the electric field break covalent bonds. Is this a new phenomenon we learned in 314? Or you learned a similar effect in 306? We didn't learn that in 306, right?
No.
Now, 306, what we say is that the Ohm's law is referred to any finite conductor. So if I go here, go to early diagram, this one. See if I can go to this one. What it says is what? The energy diagram wise, band diagram wise, okay, generally speaking, it's crystal. We can physically almost describe the same. What's different is this. For insulator, the band gap is very large. So it's hardly you can break a covalent bond to create electron holes to conduct current. So that's what the insulator is about. For semiconductor, it's easier because our band gap is small. You can do that, okay? Particularly when we doped N material or P material. How about the conductor? Conductor says what? You don't need to lift electrons from valence band to conduction band because what? Conduction band is already filled with electrons. That's what this is about. If I talk about anything, what happened in the 306 is a resistor. 306 resistor says what? I already have electrons in this band. They are available free, so they can move. Once they put in a little bit the voltage, they can move in one direction. If I flip the voltage in the other way, it moves the other way. Nothing about it difficult or not difficult because the electrons are available in the conduction band. In semiconductors, it's a totally different story. You have to create charge carriers. If you don't have charge carriers, no electricity, no current. Any question?
No.
Okay, so hopefully I answered that question.
Yeah.
Okay, let's go back to the reverse breakdown. Here, let me put you back into this page. this page, summarize. Okay, here. I want to compare. So this previously I described what happened to diode. Okay. Diffuse current coming from the majority carriers. When you have a positive bias voltage, okay, this voltage can shoot up exponentially, very high. So for full bias, this term is very large. So you have a large diffusion current, but large diffusion current coming from the majority carriers. Under reverse bias, this term goes to zero. All you have the current is from the minority carriers, which is very little. So okay, on the other side, you have a little current. So this current can shoot very high, but reverse bias, this current okay, is a negative, but very small. So that was saying is what? The diode current we described in this side is contributed from the majority carrier. From this side, really contribute from the minority carriers. All right? So far, so still consistent what we learned, okay, from the majority carrier and minority carriers, what they contribute, which one contribute to which current. The reverse breakdown is a completely additional physical phenomenon. It breaks the covalent bond in the space charge region under electric field. So this mechanism is not the thermal generation. So has nothing to do with the concept with majority carriers or minority carriers. They are actually what? Excess carriers. Okay, emphasize here. The reverse breakdown current coming from excess carriers. They are generated from breaking covalent bond by electricity, not by occur a little bit random. We don't know specifically when it will occur, but at some point it will occur. Okay, sometimes occur early, sometimes occur late.
Professor? I don't know if you can hear me, but I think your mic's cutting out a little. I think your mic's cutting out. Connection problems, probably.
On desktop, it looks like whenever we can see his little yellow triangle on his name, that he's cut out.
I see. Mine or someone else? Oh,
Yeah, you
video.
were cutting out.
Oh, I cut myself. Let me just close the video, okay?
Yeah, we didn't catch the last minute of what you just said.
Okay, let me just repeat. This behavior under full bias, the current coming from the majority carriers. Under reverse bias, charge carriers coming from the minority carriers. Get it? Okay. As I said here. Okay. Under full bias, the current is very large. Okay. They contribute from majority carriers. Under reverse bias, distance goes to zero. The current is minus IS. They're coming from the minority carriers. Majority carriers contribute to this side, minority carriers contribute here. They are exactly balanced at the zero bias. But on the reverse breakdown, the carriers not coming from majority carriers, as we described earlier, not coming from minority carriers, as we described earlier, but coming from a different part of the carrier generated. It is generated as well. You break the covalent bond by the electricity. So they are the nature of called the excess carrier. So this reverse breakdown current is from the excess carrier generated from the breaking covalent bond by the electricity, specifically in the space charge region, not by thermal excitation. So here I have another diagram I was trying to use here. Okay. When we say majority carriers, means majority carriers, electron in this region, holes in this region. When we talk about the minority carriers, we talk about the holes in this region and electrons in this region. But the carriers contribute the reverse breakdown current. There are none of the carriers coming from here and here. Their carriers created here. But we already said this carrier we are called the depletion region. Right. That's why when you, without before you break the covalent bonds in this region, you don't have a carrier. But the electricity, electric field can break a covalent bond in this region and free up the electron and holes and give up the called reverse breakdown current. Okay. Any questions? So that's what previously I want to say. And this breakdown voltage can vary device to device, can range from a tens of volts to a few hundred volts, or maybe up to 1,000 volts possible. Okay, this breakdown voltage we call the peak inverse voltage. Just say you go beyond this voltage, diode will become reverse breakdown. However, this reverse breakdown voltage is we don't know any given diode, we don't know when it will become reverse breakdown. We just know sooner or later you will get a reverse breakdown. However, for the Zener diode, okay, what we're saying is the reverse breakdown voltage by design and fabrication process control, we can specify it. Okay, maybe at a -3 volts and -10 volts or -20 volts, we can design that. So that's the breakdown voltage. And this breakdown voltage is saying that the breakdown voltage is more specifically is that when it begins breakdown, so that's a quantity V sub ZO. That's reverse bias when it will begin breakdown. But once breakdown, the current goes to very, very fast. Small amount of voltage, okay, beyond the reverse breakdown voltage, you can create a huge reverse breakdown voltage current into this vertical line very, very quickly. And this diagram shows it's a normal diode, but if you want to use as a Zener diode, you reverse bias it. Your plus side polarity line up with this side, and negative side polarity line up with the triangle side. And IZ is defined as following opposite, so that VZ in terms of polarity wise really just opposite of VD. IZ current is defined the direction as opposite of IZ is opposite to ID. Just opposite way. Okay, so IZ is the reverse breakdown current. How big this current is? Well, eventually the current circuit has other resistors will eventually limit this amount of this current. Okay, we call it breakdown. The question is, will this breakdown damage the device? Well, sooner or later it will damage it. What's the damage? You don't want this current to be so large. If this current is so large, it would, because Ohm's law, it will generate the heat. And once you generate heat, you melt the diode. Once you melt the diode, it's done. You toast it. Okay, you don't want to do that. So this is reverse breakdown. But before you hit a reverse breakdown, well, in this region, the behavior is just as a normal diode. So the Zener diode is used, behaves as a regular diode before the reverse breakdown. Used before reverse breakdown, Zener diode is a regular diode. Any question? Okay, now we learn the basic. So how do we solve the circuit? So to solve the circuit, well, you combine the Kirchhoff law and device law. So this is a simple circuitry, bias voltage, resistor, in series with diode. So Kirchhoff law says the voltage V is PS plus the voltage drop at the resistor, which is RD, ID is the current in the Ohm's law, and plus voltage drop at the diode. You have the device or the diode, the resistor, so that's the device law. And how the device law of the diode? So that's what you use this. You combine these two equations, you can solve the voltage current in this circuit, given the value of amount of voltage and the resistor value. And this is a nonlinear relationship. You cannot solve as we are able to do that in 306. And 306 Ohm's law is a linear law, so you can solve the circuit analytically, get the solution. And here you just have to use the iteration, try and error. You set the initial current, and then you calculate the voltage, and then to see whether those voltage current satisfy this equation and this equation simultaneously. Okay? Or you can say you substitute ISD into here. You have a single equation, Vp equal to R IS in this factor and VD. So it's a single transcendental equation of a V sub D. You have to try the value of a V sub D to find the solution. Or you can do that graphically. Graphically, the same is what? I can rewrite the device law into this form. And then this another, I can rewrite the Kirchhoff law, voltage law, into this form. And this is a diode device law. Both the relationship between diode current and diode voltage. Diode current, diode voltage. So I have a pair of value, quantity, diode current, diode voltage. They must simultaneously satisfy the equation. If you satisfy one equation, this equation is linear with a negative slope, then the solution must be on this line. If you satisfy this equation, the solution must fall on this line. So if you satisfy both equations, then solution is set at the intersection of the two lines, two curves. So that's graphical approaches. Or you can use computer simulation tool to do that. Behind the simulation tool, still the algorithm approach is either by the area and try or graphic approaches. So one homework problem asks you to do this, and that's all. And later we will learn using different model. So what's a different model? Different model is this. Piecewise linear model. Okay. Approximate what we're saying is what is a simplified diode device. So this is a huge nonlinear effect, the behavior of the relationship current voltage relationship law. We approximate by a few linear line. One linear line from here to here, straight to the zero. One linear line, we approximate zero. That's before the breakdown. So V gamma is when diode voltage is below V gamma, we say diode is off. It's this line. ID is zero. When diode voltage is above V gamma, we will see the current, and current increase linearly. So mathematically, linearly, that equation describes what happened in here. So inverse, the slope is equal to inverse of RD. And this expression of the piecewise linear model can be rewrite into this form. They say is a voltage, diode voltage equals a constant amount, turn on voltage, V gamma, plus a diode forward bias resistor, RF, times ID. And this forward bias resistor is very small. Basically, when the diode is turned on, it's a very little resistance. And turn on voltage is a very small fraction of a volt, okay, 0.6, 0.7 volts for silicon. Any question? Okay, so there are a few different versions. Okay, one version is V gamma is non-zero, 0.7 volts. RF is non-zero, maybe 10 ohms. So that constant voltage drop there's a constant voltage drop times the voltage drop at the resistor here. So that equation exactly corresponds to this device model. We use the device, we learned from 306, we can model the diode behavior. Of course, when the diode voltage is less than V gamma, diode is off. Once diode off means what? The diode break. There's no current conducting through. So there's no current conducting through. If voltage is less than V gamma, when the diode is conducting, it shoots up very quickly. Another simplified model, we say, well, we'll approximate the small resistance be 0. So that means that the terminal voltage is non-zero. So still this line, if the RF is 0, the inverse RF will be infinity. So this line it shoots up just vertically. Okay. So in this model, RF is 0 means there's no resistance here. It's just the diode has a constant voltage step down V gamma. So this on that model, off model is just a break open circuit. Okay. Another one model is even simpler. V gamma is equal to 0. That's sometimes we call it ideal model, ideal diode. So that basically is this model, but term voltage shift from the finite V gamma to 0. So it's here. Okay. Basically, on the forward bias, diode is on. There's no resistance. It's just a piece of a conductor. On the reverse bias, diode is off. It becomes open circuit. Any question? No question. So this one tells you the simple way to model the circuit. Okay, this same circuit as previous. And then the two equations we derived early. This is Kirchhoff law. This is diodes device law. But if you use a piecewise linear model, what do we do? So this is piecewise linear model. And the voltage, high voltage, the voltage drop at the resistor, and voltage drop at the diode. But the diode device law is a VD equal to V gamma plus RF times ID. So this equation, you substitute VD here, you can solve ID. ID is this value. All this is under if the diode is turned on. So VP must be greater than V gamma. Diode is on, you have this solution. If you ask if a diode is off, if a power supply voltage is less than terminal voltage, if power supply less than terminal voltage, the diode becomes open circuit, current will be 0. Any questions?
Professor, if you could go back to the last slide.
This one.
Yes. So for the bottom left diagram, it says that the diode voltage, if it's 0, the diode current is greater than 0. But when we looked at the graph previously, isn't the graph going through the origin? So how is the current greater if the voltage is 0?
No. It said this. It's approximate the original nonlinear relationship by two different linear relationships. So this is not truly the true diode. True diode is the previous the equations we get is this guy. Okay? That's cross the zeros here. But here, we approximated this one by linear line, and we almost saying, like, okay, let's see. We approximate this part by the straight line. We say, that's you have a current. We approximate this part by another line. This current is small by 0. It's approximation. It's not a true device law, not an accurate device law. It's approximation. I said approximation, approximation. Did I answer your question?
Yes, so the diode current is equals to the reverse bias saturation current when the voltage is 0, right? That's the small current that's present when the voltage is 0, right? Like
This is still a little bit, no, okay. I would say, okay, I kind of recognize, okay, I copied the drawing from the book. That's what this is. But what really this one is I can say, create a confusion wheel. This current is before we approximate. Before we approximate. This line, okay, whatever this one is, really is this one. That's the accurate model. The piecewise linear model follows the red. It's 0. Okay?
So when the voltage is 0, there still exists a small current, right?
No. On the piecewise linear model, we approximately equal to 0. It's here. If voltage of diode is less than V gamma, we model the diode current is 0. Only when diode voltage is above V gamma, we model with a diode current. It's
But does that
approximation model.
contradict the diagram we saw later?
Pardon me?
Does this not contradict the diagram we saw later, like the last slide we were in?
See, this one and this one is this is straight line here. Ignore this okay corner. What I say is it is one straight line here and another straight line here. That's exactly one straight line here, another straight line there. Ignore this actual corner.
Like the bottom of this slide, 28. Yes, the bottom left.
Bottom left, this one?
Yes, you see the current is greater than 0 if the voltage is 0, but that contradicts what we learned before.
Current is 0. No, current is non-zero. Current is non-zero. What do you mean current is 0?
Right, but isn't it supposed to be 0 because the current is only greater if we are past that gamma line?
Oh, you have to think about what we're saying is we model this side dial on, we model this side dial off. Clear? Dial on, dial off. Once dial on, dial off, it shoots up very quickly. But what we model is shoot up quickly is because the RF is non-zero. But when you model RF is 0, this shoots up vertically. So vertically, voltage is V gamma, voltage equal to V gamma, but the current can go non-zero. But this model just say we further simplify model, they shoot up the non-zero current at this point. So this basically is a break point. Okay, once external voltage is slightly above V gamma, it current shoots up, but we model that the break point at V gamma equal to 0. Did I answer your question?
Okay, yeah, that makes sense.
All right.
Okay.
So this you really think about this sort of a straight point, the break point. Okay, just okay. Physical voltage must be greater than 0, but we model it as well. You have a finite current start shoots up at the voltage equal to 0. All because this straight line is not tilted, but vertically increased. And this vertical increase is not vertical increase at V gamma, and we model it vertical increase at V equal to 0. V equal to 0. Okay?
Okay,
Hello?
thank you.
All right. Okay. Any questions? So if no questions, so hope you're able to do homework during the weekend. Okay? I will see you next week.
Professor,
Yes, please.
question about what the voltage and current here mean. Does that mean for any given voltage, that will be the amount of current that will flow through, or that amount or less will flow through? Or is this the amount of